Good day to you. Thanks for joining our webinar today on the topic of understanding arc flash hazard analysis. My name is Banu Srila, and on the call here with us today is John Kolak, our guest speaker and presenter. As many of you know, John is an award-winning author and a safety consultant, and he is the president of Praxis Corporation. John has over 3 decades of experience in electrical power systems, and also he is a consummated safety professional. Arc flash hazards and incident energy calculations are a major portion of NFPA 70E consensus standards. So this webinar will be in 2 parts today. John will cover the basics of electrical arc flash and arc flash risk assessment, key elements of the arc flash risk assessment, and also a few important definitions, training topics, and also the limitations of these assessments as well. I will touch on some product solutions that Grace offers to mitigate the arc flash risks at the end. As you go through this webinar today, please type in your questions using the questions pane on your webinar console, and we will answer them at the end. Without any further delay, I will turn it over to John. Thanks.
Thanks, Banu. As Banu said, I'm John Kolak, the president of Praxis Corporation, and I'm going to be talking about the ins and outs of arc flash risk assessment studies, and I'm really going to be covering it from 2 perspectives. Of course, we'll be talking about it from the electrical engineering side, which has to do with not only how to conduct the study or perform the study itself, but also how to communicate the results of that study to the decision makers who have to use this information. I'll also want to be talking to the journeyman who might be listening to this presentation, because there's a lot of great information from the working man's perspective that's very useful and often goes underutilized in these studies. So we're going to be talking about that as we go out through this presentation as well. And again, what I'll be talking about, we're going to begin with a discussion of what we know about electrical arcs, in particular how that information is useful in developing protective systems for workers who are exposed to electrical arc hazards. I want to talk about the limitations of an arc flash risk assessment study. There's a lot of things the study does well. There's a few things the study does not do at all, and we want to make sure and cover that so they're properly integrated into the protective systems associated with the study. We'll talk about the various elements of the arc flash risk assessment study, ranging from the system modeling to the short circuit studies, ultimately with the incident energy calculations, and probably most importantly, the reporting element. We'll talk about that. That's critically important and often is the most useful part of the presentation for management. We're going to be talking about a few ARC-related definitions that you probably already know if you're familiar with the NFPA 70E, but we'll touch on that for those that may not be. A very important subject will be the training. What kind of training needs to be associated with the study and the arc flash hazards as well. We'll talk about, for your engineers in particular, we're going to talk about avoiding some arc flash risk assessment traps. Common things that engineers do that end up not working out very well in the end. We'll cover that for the engineering in the group, and then we'll give you some recommendations. And of course, you can type your question and answers, or type your questions rather, into the question box, and we'll do our best to answer those either right away or at the end of the presentation. Let's go to the next slide. Some definitions to add to your vocabulary. Well, of course, incident energy is one of the most important definitions, and incident energy is measured in 2 ways. Here in the U.S., it's measured in calories per square centimeter, and more in Europe, it's measured in joules per square centimeter, which is more of a mechanical part of the discussion. In the U.S., the magic number for the number of calories per square centimeter we're interested in is 1.2 calories. 1.2 calories per square centimeter of your skin will render you a 2nd-degree burn. In the picture on the right, you can see the fellow's arm is burned. The middle of his bicep there, you can see the tissue has been burned and it's blistering. That would be what would look like a 2nd-degree burn. Just for background, a 2nd-degree burn, if you want to know what 1.2 calories really is, it would be the equivalent of putting your finger over a standard issue candle, hold it 1 inch above the flame, and hold it there for 1 second. And that would give you 1.2 calories of heat, which would give you the onset of a 2nd-degree burn. For the purposes of our discussion, we're going to always be considering arc flash hazards to be 1.2 calories or more. A number that you won't find in the regulations that I recommend you make note of is 10.7 calories per square centimeter, will result in a third degree or an incurable burn. And so this is important for people to understand, because the burns at 1.2 calories or more will give you a second degree burn, but it's a curable burn, as we say, because it will cure itself with just normal first aid. You don't need skin grafting or anything like that. Once you get above 11 calories, you are in the realm where you actually would lose tissue and lose function forever. So it's an important number to keep in your brain as you work through this. Arc rated versus flame retardant or flame resistant. Arc rated has two primary differences between flame retardant or flame resistant clothing. One of them is the way it's tested. An arc rated outfit is tested when exposed to an electrical arc, which has a different kind of heat gradient to it than, say, a fireman running into a burning building. And it also includes something that you see on the bottom, that E sub BT, which is called breakthrough energy. That's the blast part of the discussion. So normally when we're talking about electrical safety on the job, we're going to be talking about using arc-rated clothing, not just flame retardant or flame resistant. Then you'll see the ATPV value, the arc thermal performance value. That is the same as an arc rating. So if you see that in the regulations, that's what it's referring to. And then, as I mentioned at the bottom, the E sub BT is breakthrough energy. That is the blast component of the arc. And so, of course, with arc blast energy the way it is, getting an arc flash going could blow normal clothing right off of your body, leaving you unprotected from the arc flash hazards that are there. And so, of course, arc-rated clothing needs to be strong enough to withstand the blast, as well as insulated well enough to protect you from the heat exposure. Let's go to the next slide. Some of the limitations of arc flash risk assessment, and this is extremely important. The first one is the most important point on the whole slide, and that is that the engineering software that we use to do these calculations will use the manufacturer's protective device clearing times for calculating incident energy. That means that the circuit breaker in particular that would be protecting a circuit would operate at the same speed it did when it was brand new. So some of you may be working in facilities like steel mills that may be 100 years old. Some of the equipment could easily be 50 or 60 years old in those environments. And of course, in those situations, if you don't have an extremely aggressive maintenance program, the chances of a circuit breaker that's been in the closed position for, say, 20 years, operating at nameplate speeds is pretty remote. So point number one has to do with electrical maintenance, and I cannot overstress the importance of that maintenance program, because if those breakers are even a little bit sticky and they open up slightly slower, you'll notice the incident energy goes up exponentially. So very important point on the slide. The engineering who does the work, it would benefit if you have engineers who have a field background, meaning they've actually done work for a living, for example, like an electrician or electrical technician of some kind, or at least had worked in an environment where they work with workers, because there's a lot of interpolation that needs to happen with the study. And it helps if you have a background to do kind of a common sense check there. And that's really the last point, the idea of a reasonability check on the software outputs. Most of the time, the software does an excellent job. There are a few times when you'll get an anomaly, and you have to have enough experience to notice that just by looking at the data. Let's go to the next slide. Now what you see here is the three components of what we call arc clearing time. And in the most simplest terms, an arc clearing time means it's the duration in time, in seconds, from when the arcing event starts to when the arc is extinguished. There's three components to that, and you can impact two of the three. The first one is the fault sensing. How long does it take for the overcurrent devices to recognize that the current flowing in the system is in fact not okay? It's a fault rather than just load current in the system. So that has to do with your overcurrent protective device settings, and we'll talk about that at length. But overfusing or changing the overcurrent settings can result in catastrophic arc flash events. We'll talk about that in an upcoming slide. As I mentioned, the protective device operation, how fast it actually operates, is mostly a function of maintenance. And this is true primarily of circuit breakers and the like. Fuses normally don't suffer from that problem, but normally the protective devices like circuit breakers absolutely need aggressive maintenance. And the third element of the arc is the arc extinguishment element, and that has mostly to do with the interrupting media. In other words, whether it uses oil to interrupt the current flow or gas to interrupt the current flow, how does it actually make the arc extinguish? Normally you can't impact that too much, but you certainly can impact the first two. Let's go to the next slide. Now, the elements of an arc flash risk assessment, the system modeling part is by far the most time-consuming part of the process. Probably 60% of the entire man-hours dedicated to the study will be in gathering the data for the study itself. And that goes hand in hand with the data entry and in particular data validation to make sure that we have the correct data in the software itself. Then the system analysis part of it is really more using the computer models to generate the various data points we need to evaluate the system, both in terms of short circuit current flow and our incident energy calculations as well. So the systems analysis is also a very time-consuming part of the analysis. And again, where a seasoned engineer would make quite a difference. The reporting and recommendations is perhaps the most important part of the study. And I see this mostly misused. If there is a part of the study that I see misused, it would be the reporting. Namely, the engineers do not make the study understandable to non-engineers. And we'll talk about that in the next couple slides. But that's very, very important. And then we'll talk about the equipment labeling requirements. Pretty simple there, but we still should just talk about what it means. And I'll show you an example of an arc flash label. And then we'll talk about the training components, the various things we need to do to train people on the study itself, and then the arc flash hazards that they're going to encounter on the job. So let's go ahead and go to the next slide. What you see in front of you is just a snippet of the low voltage part of an arc flash risk assessment study. Now again, this is only there to give you an example. And what you're seeing here is a 250 kVA transformer installation that has a high voltage, high side fuse, which is labeled 50N volt transformer. The transformer itself, and then underneath is the low voltage or the 208 volt fuse, which in this case is labeled FS-7. Now, what you need to understand about the system modeling component is that it is normally we only include things in the system model that impact the incident energy calculations. So we don't normally put in things like solid blade disconnects or devices that don't interrupt current flow because they have no bearing on the incident energy. So a system model schematic diagram or diagram is useful electrically from a troubleshooting standpoint, but it is not the same as an electrical schematic diagram you would use for troubleshooting. So just kind of keep that in mind, those of you who are working people. Now, I mentioned at the bottom of this slide that this part of the process can be done by a technician. It does not need to be an electrical engineer to do this. In fact, we've had excellent luck using electricians to gather data. Once we got them teed up with the forms and things they need to gather and capture the information we need, electricians have done an excellent job gathering data. In fact, they know the system much better than the engineers usually. And as such, this is something that they can do. It lowers your cost of the study, and it's also probably even better than using engineers for that step. So for what it's worth, that can be done by a technician. Let's go to the next slide. What you see in front of you is a low voltage circuit breaker spreadsheet. What's important, one of the wonderful elements of an arc flash risk assessment study is these spreadsheets have all of the information that you would need to, for example, if you blow up a circuit breaker and it is unidentifiable what was there, you can look at the spreadsheet to find out what was there exactly, the make, model, style of everything, the trip settings, everything is available to you right there. So from an engineering standpoint, it's useful from that perspective. From a troubleshooting standpoint, for the workers, we can also tell if somebody has changed the settings in the field. And you can simply compare what you see on this spreadsheet to what you actually see out in the field. And if there's any changes, that means those have been changed since the study was done. And I'll talk about the significance of that from an incident energy standpoint later in the presentation. And this step also can be performed by a technician. Gathering the data and inputting the data can easily be done by an electrician. Let's go to the next slide. Now what you're seeing here is the short circuit calculations on the system. And again, if you look at this, these numbers are in thousands of amperes. So like under the 50N PDPL bus, it's listed as 18.111. That would be 18,111 amperes of current flow. So this is the short circuit part of the study. It is important to recognize that the entire arc flash risk assessment study begins with the short circuit calculation from the utility company that feeds the plant. And so they will do a calculation usually on your incoming high voltage system, and then it would be incumbent on us engineers to take it from there down to the bottom of the study. So the short circuit calculations are very important, in particular to something called equipment duty, which we'll get to here in a slide or two. This step really should be performed by an electrical engineer because sometimes there are some anomalies we'll get in the calculations, and it would really take an engineering eye to catch those. So this step really should be performed by EE. Let's go to the next slide. What you see here in most arc flash calculation software have some version of this. The software we use calls this equipment duty. And equipment duty compares the interrupting rating of a protective device to the actual short circuit current to which it will be subjected. And this is so important because we never knew this when I used to do the work. But there are a number of devices, especially if you work in an older facility, that may not be able to interrupt the current flow to which they're subjected. And if you were to reset that breaker now, it would likely result in something called a through fault, which would probably result in an arc flash event. So for example, here we see a system that the rating of the device is 25,000 amperes of current flow. It's actually subjected to 35,885 amperes, which is 43% over duty or over its rating. So from a worker's standpoint, this equipment duty report, I would have this on my person pretty much all the time when you're troubleshooting, because the deal is you never ever reset a circuit breaker on something that's 90% of its duty rating or more. So this is something, as I said, when I did the work, we often would reset devices into situations which could be catastrophic, and as a result of that, this information is very useful, and this step here also should be performed by EE. Let's go to the next slide. Now, this is a little bit technical here, but this is perhaps one of the most important parts of the presentation. What you see on the left here is what we call a time current characteristic curve, or a TCC curve. Those two, the magenta colored footprint, if you will, and the blue colored footprint are actually the time current characteristics for the various circuit breakers involved in this system. So if you look to the right, sub number 2 bus B is protected by a GE standard breaker, a 3,000 amp breaker with a 2,500 amp plug. That time current curve there, set the way it is, will calculate, as you can see, 2.9 calories of heat per square centimeter. So the incident energy is 2.9. In other words, if you were exposed to that with bare skin, you would get water blisters in your skin, but it would still be a curable burn. Now, what I'm going to do here is simulate somebody doing something stupid out in the field. In particular, if they get what they think is a nuisance trip, they could change the overcurrent settings on that breaker, that trip settings on that breaker, and I want you to see what happens. Let's go to the next slide. Now, this would be something, as I said, would occur if somebody had what they thought was a nuisance trip. In other words, sub 2 bus B tripped out, and they thought it was a mistake, that there really wasn't a fault, that the system tripped out accidentally. And if they dial that up just a couple of clicks on the current, they didn't take it all the way back to maximum settings, look at what happened to the incident energy. It went from 2.9 calories to 66.4 calories. Now, 66 calories is pretty much certain death if you get exposed to that amount of current and the blast associated with it. And what's so important about this is that this is actually a study I did myself. There is a label on sub 2 bus B that says 2.9 calories to this day. And that is true, providing that nobody changed those settings. So this is probably the accident of the future, where somebody may change the settings on a device and they are actually not thinking about what it might do to the incident energy there, and it could produce a death trap for somebody else. Now, I will also be careful to tell you that if you don't maintain your circuit breakers, you'll get the same result. That breaker could be delayed in its tripping, retarded in its tripping time, and you could have way more incident energy that's actually there than what you see on the label. So that's an important point, and I can't overstress the importance of it because this happens on the job sometimes on purpose, where people have nuisance trips, and sometimes inadvertently because of maintenance deficits. Let's go to the next slide. Now, what you see here is an incident energy calculation spreadsheet. Now, something that I recommend that we engineers do, which is what I've done here, is I've sorted the data for the customer in descending order from incident energy, but I've also highlighted things in red where the breaker timed out. And what I mean by that is, take a look at the little arrow there. I've got pay attention to arcing time. The 1584 calculation methodology normally says we're going to limit the calculation time on an arcing event to 2 seconds or less. Their logic is that most arcs last less than 2 seconds, which is true, they also think that a person wouldn't get out of the arc if they wouldn't stay in an arc for longer than 2 seconds. And only somebody who doesn't work for a living could come up with that idea, because the truth of the matter is that when you get involved in an arc flash, by the time you realize what happened, it's over. So here's the deal, and I've highlighted it in red for my customer. Anytime the arcing time is 2.001 seconds, what that means is we have stopped calculating incident energy at 2 seconds. It doesn't mean the arc goes out in 2 seconds. So if you remember, putting your finger over the candle for 1 second will give you a burn of 1.2 calories. If you kept your finger there for a period of seconds, you would get second and third and even fourth degree burns if you let it stay there long enough. And so the point being is, anytime you see 2.001, I want you to perk up in the arcing time set element, because what we're calculating is 128.5 calories if it cleared in 2 seconds. If it didn't clear for, say, 15 seconds, that might be over 1,000 calories. So pay attention to the spreadsheet, especially the arcing time column, and be aware of anything that's at 2 seconds means it timed out. It didn't trip out, it burned in the clear. And that would mean that the labels are understated, is what it basically means. And of course, this step should be performed by a double E. Let's go to the next slide. Now this, as I said, is I think an area where I see probably the greatest opportunity for engineers to make a difference. Oftentimes when our company is hired to do a rear-end review of someone else's study, we often notice that they don't have a narrative report, or if they do, it's written only for engineers to be able to understand it. And of course, the decision makers that are going to fund or implement the changes we recommend in the study often are going to be non-engineers. And so we need to make sure that we write these reports in language which is understandable to anybody. And then that would give a better chance of implementation and makes the study more useful as well. So, of course, I put in bold letters, the arc flash risk assessment report must be easily understood by non-engineers. And, of course, this should be written by a double E. And I would also recommend you do something called the layperson check test, engineers. So we give the report to somebody who's a non-engineer and ask them to tell us what they think it means. And if anybody can explain it back to you and it's pretty close to what's there, we did our job well. So let's go to the next slide. Now here I've got an old arc flash label. It's actually an outdated label, but it's the best picture I had of an arc flash label. And here we see the calculated incident energy at 97.5 calories and the various approach boundaries that those of you who have had in the NFPA 70E training. Now the one that went away is the prohibited approach boundary. That no longer exists. But this is an example of a slide that has all of the required elements you'd have on the requirements in the 70E labeling requirements. Now be aware, arc flash labels are required anytime there's a piece of equipment that would require servicing or maintenance in the field. So if it's going to be accessed in the field, it really needs to have an arc flash label on it. And the information that you see on the label is stipulated in the 70E. And this step, I said, should be performed by a technician, meaning installing the labels, because once again, the electricians have a much better grip on the names of the equipment in the field. And again, it's possible that, and even probable in places in older facilities where there have been multiple labels on the same piece of equipment. So the electrician on site would be a better resource for that than even the engineers. So I would recommend the labeling be done by a technician working in concert with the engineer who did the study. Let's go to the next slide. Now this slide relates to our previous discussion that we had about incident energy going from 2.9 to 66 calories. And the point here is that you have to have some kind of a change management process to alert the engineers who did the study when components of the system have changed. And now that can happen either because you've added or subtracted load, and in particular larger loads, motors of maybe 20 horsepower or more, transformers of say 30 kVA or more. If you add or subtract those loads, either one, we need to know that from the engineering side of the house. If any of those overcurrent devices have changed and they have not been able to be replaced exactly in kind, so say you blow up an old Federal Pacific breaker and now the replacement might be a Cutler hammer breaker, in those situations you need to let the engineer know that it's changed and work with the engineer to develop a new set of device settings to make sure that we either have an equivalent protection or perhaps even improve the process. So some of my customers use a pink slip that you fill out when there's a change, so it highlights anything in pink. The engineer would know that that's an urgent thing. It's a change that has happened and we need to rerun the study. And so the change management process, extremely important. And it's a place where the field, the workers integrate or communicate with the engineers who did the study. And together we come up with the changes that make the system better. Let's go to the next slide. Now the training topics, well, of course, there are some required training elements that are included in the 7E and also just general training requirements from OSHA. But first of all, we need to tell our workers and teach them and train them about what is actually the purpose and function of the study itself, including those limitations we talked about earlier. Of course, they need to be trained in the NFPA 7E, which is a safe work practice document. The NEC is the National Electrical Code, also known as the NFPA 70. And then for those of you that work on transmission and distribution systems, the National Electrical Safety Code, but that wouldn't apply to too many of you listening to this study. Of course, we need to teach them how to interpret those arc flash labels, what do the various numbers mean, and how to select, test, use, and maintain the proper equipment associated with that, which is the next point. How to use that change management process is also an element. When to use it, how to use it, to make sure they've communicated completely with the engineers doing the study. Emergency response needs to be part of this. How do we rescue somebody who's been involved in an arc flash event? Remember, the temperatures of electrical arcs are second only to a laser on planet Earth as being the hottest thing on Earth. They're 4 or 5 times hotter than the surface of the sun. If you're exposed to an extreme arc flash event, even if you're wearing arc-rated clothing, the concussion, for example, could cause injury as well. We have to be able to rescue each other, and there's elements of that in the 7E book as well. And then finally, alternative means of arc flash protection, and we'll talk about that here in the next couple of slides. So let's do that. Let's go to the next slide. From the engineering recommendation side, there's really 3 things that we can do primarily to make our situation better for our workers. The first one is to increase the working distance on the system that we're working at. So for example, anything you can do to add some distance between your chest and the arcing terminals of the equipment, you could do it. And we'll talk about how to do that here in a little bit. The use of dead front equipment, meaning there's a solid barrier between you and the exposed parts at 50 volts AC or more. So we'll talk about what that looks like and some of the limitations of that. And then probably the most important thing we can do from the engineering side is to decrease the arc clearing times. So let's go ahead and jump into this and talk about those issues right now. Let's go to the next slide. Now, increasing working distance. There are several ways to do it. One of them is for those types of breakers that operate on a pistol grip contactor, on a panel cover, panel door, if you will. There's no law that says those things have to be right in front of the device that actuates. So if you have the choice of relocating those pistol grip contactors, even 4 or 5 feet away from where it is now, 20 feet would be better, that would give us additional protection. So if they reset a breaker or whatever and it blows up, having some distance between you and those arcing terminals is a great idea. Using supervisory control and data acquisition systems, often this would be fiber optic systems, to be able to reset a breaker, for example, from a control room rather than doing it while standing in front of that breaker. Again, a great option. Some companies have used timed relays, meaning after you close the switch in, and when you actually actuate the handle to close it, it actually just starts a timer, which will give you, say, 15 seconds to get out of the way, and then it'll close the breaker in a retarded fashion. Again, a great option if that makes sense for your facility. And then the use of fiberglass reinforced plastic tools. These are the switch sticks you see here on the right. Typically, those are only used on high voltage circuits. But hey, if you're working on a piece of equipment that is set up to be using one of these devices, even adding an extra 2 feet will improve your situation dramatically. So increasing working distance is always a good option if you can. Let's go to the next slide. The use of dead front equipment. Well, what you see on the right side of the picture on the right is what used to be a dead front panel cover. It's a 4160 volt system, but don't confuse this. This can absolutely happen at low voltage as well. But here you see that an arc developed behind that door that lasted longer than 2 seconds, and it melted a hole in steel. And there was enough residual energy that came through that hole that was made by the arc to actually injure or kill the person who was standing near that. So please understand that dead front equipment are a huge improvement. It's a great idea to have it, but don't assume that that dead front can always stop the incident energy in the middle. And again, this is where you'd see those arc clearing times of 2.001 seconds or more. That kind of an arc would be the sort of thing that would do what you see here in this picture. So with that said, including engineering specifications in your company's safety program, procurement specifications, in other words, speccing out the kinds of equipment that we want from the engineering side, that may be using arc resistant construction styles or frames or other types of systems that would be better. That's what we've got under the second point. Ensure that the safety features actually work on the system. There have been situations where we've had events where they've had dead front doors where the equipment was malfunctioned the way it was produced, and you actually had to open the door to access to do the racking out of a breaker inside the enclosure. It actually had a safety feature that didn't function. And then, of course, another option would be moving test ports to the face of the equipment. And I put Grace products there in parentheses because that's a huge benefit of using these products, is that you can work through a dead front. So don't get me wrong, that dead front that you see in the picture there, it used up a bunch of energy to melt that steel. So the situation was better for whoever was on the other side of it. But in this particular case, the arc lasted so long that there was enough residual energy that the heat was, I think, that caused the fatality, if I'm not mistaken, in this event. Let's go to the next slide. Decrease clearing times. Well, there are several things we can do, and I don't want to go into the engineering weeds too deeply here. But in terms of shortening the arc sensing time of the arc time continuum we talked about earlier, one thing we can do that really improves our situation is to use electronic relays. If you have breakers that, if the system is critical enough to do this, electronic relays are much faster than thermomagnetic relays often. And in those situations, we'd want to use those if we could. So using electronic systems are faster than other mechanical systems. Fiber optic sensors, if you're having trouble with finding overcurrent settings that coordinate for you engineer types, fiber optic sensors work great because they don't need coordination to work. They actually sense an arc flash. They sense a flash event and a preset amount of current flow. It has a Boolean AND gate between them for you engineering types. And if it sees a flash of light and a preset amount of current, it interprets that as a fault, and it will clear the system pretty much instantaneously. Using differential relays, it's like a GFCI kind of a system, but a differential relay compares incoming and outgoing current flow. And again, for protecting things like transformers or buses, they're particularly fast. And the faster they are, of course, the better it is from incident energy. And for engineering types, avoid double transformations if you can. So, for example, if you have a system that goes from, say, 12,470 to 480, and you need to go down to 208, it would be better if you could to go have one transformer for the 12,000 to 480 and a separate transformer from 12,000 to 208, rather than have a transformer from 12,000 to 480 and another one from 480 down to 208. It will turn out better from an instant energy calculation to avoid that if you can. So again, I apologize if that gets too technical for those of you listening. I'm speaking there primarily to the engineers. And then finally, decrease clearing times. Well, eliminate overcurrent devices. That would help. If a device is not able to interrupt the current flow, it means that the next upstream device is going to do that, or you're going to melt something. And either way, it's a longer lasting arc than we want. So eliminating overduty devices is a good idea. Once again, those electronic breakers we talked about earlier are really a good idea. If you can use current limiting fuses, those are if you have a lot of fault current in your facility, a lot of short circuit current limiting fuses are a godsend. They do a great job at lowering incident energy. Most often when you have high fault current and a current limiting fuse, the incident energy is 1 calorie or less often. And so they're really a good device. And for those of you who work on more high voltage systems, sulfur hexafluoride or SF6 breakers are often a good option. So let's go to the next slide. Okay, let's talk about some of the arc flash risk assessment traps, and this discussion is primarily for engineers who might be listening. The first thing is don't hyper-focus on the high voltage system. Oftentimes the incident energy, and in particular the arc blasts, are primarily a function of fault current, which is higher on the low voltage side of the system. So oftentimes companies exert a lot of energy protecting people from high voltage systems when in fact at high voltage, everything that you do on the system is going to be done with insulated sticks. So the truth of the matter is you get a lot closer to higher arc energy at low voltage than you do at high voltage. So focus on the calculated incident energy and manage that accordingly. Don't model a system based on voltage levels. Some companies will just stop at 480 volts and they won't go any lower than that into the system. Once again, pay attention to the calculated incident energy. We've had 208 volt systems that have very, very high incident energy levels, and we've had arc flash events on 208 systems where it blew the transformer right off the wall. And so don't assume that your 208 system is always a safer system than 480 or above, because that may not be the case. Don't assume downstream devices are okay once upstream incident energies are okay. So for example, it's possible on a 480 volt to 208 transformer, on the 480 volt side it may be 6 or 7 calories, and on the 208 system, because of the overcurrent devices, it may be 27 calories or something like that. So don't just stop at a system when you think it's okay on a higher voltage system, because again, do the calculations, make sure what you got downstream, and stop managing the process when the calories get below a set amount. And I would recommend 10 calories myself. And then finally, use good judgment when applying the results. And that's again where the experienced engineers can be of good use to you. Or if you're not an experienced engineer, the sage thing to do would be to hook up with an electrician and work with it together with them on the system as you're going through building the model, etc. Just a suggestion. Let's go to the final slide, and then I'll hand it over to Banu. So the closing thoughts. Well, the purpose of arc flash, in my opinion, is to reduce incident energy levels. You should be aware that the engineering calculation software, the engineering standards for this actually don't require us to lower incident energy. It really requires us only to create a label and properly label the system. So I think where we engineers get paid the big bucks is to lower incident energy if we can, and that's what I would recommend we do, but it's just my opinion. There are many ancillary benefits to performing an arc flash risk assessments. We found devices that were seized in a closed position that were non-functional. We found things that had been changed in the field. There were sometimes whole circuits there that people didn't know were there. There's many benefits to doing the study besides just the incident energy calculation. Use only a qualified electrical engineer to perform the analysis. With help and assist from technicians is a very great idea. And then at the end of the day, let's make it personal, folks. Let's pay attention to the fact that at the end of the day, we're trying to protect people. And so manage it as best you can, and keep in mind what we're trying to accomplish, and I think we'll get it done well. So I hope this has been helpful to you. I'm sure there's probably questions. There's so much to cover. Feel free to type those questions in, and I or Banu will answer the questions as best we can. So I'm going to go ahead and turn it over to Banu right now. Thanks.
Thanks, John, for sharing such a great information with our audience today. Let's take a quick look at how GRACE permanent electrical safety devices, or PESDs, can help you in reducing the risk of arc flash hazards. Firstly, PESDs that you see on the slide are basically simple devices that are hardwired to the source that you are trying to lock out. The voltage indicators you see on the left side are primarily used in mechanical lockout tagout for verifying the voltage presence, such as last phase and stuck blade condition. We have several options to meet your unique needs in various configurations, and they all add an additional layer of risk control for your mechanical lockout tagout to verify the voltage presence. This product again meets the step 4 of NFPA 70E article 120.5. Then performing an absence of voltage test inside the panel exposes the electrical worker to higher incident energy and arc flash hazards. So this is one of the most riskful tasks. The voltage test station and the safe test point, what you see on the right side of the slide, allows the qualified electrical worker to perform the live dead live test, or you call 3-point test, from outside the electrical cabinet using an adequately rated meter or test instrument, which meets again the step 7 of the NFPA article 120.5. You can basically perform this live dead live test under normal operation when the doors are closed and secured, which meets the article 130.5 step 4. So these devices are built with high impedance protected circuitry, which limits the maximum fault current to 2.35 milliamps at 480 volts when any two test point jacks are shorted together. Also, there's information on your webinar console on the product technical specifications, and also there's an ebook titled Benefits Beyond Compliance for you to download. This ebook has a lot of great information about NFPA 70E, including the risk reduction examples and how our products can help you to reduce your arc flash hazards. With that, John and I will stay on the call to answer your questions. And again, thanks for joining our webinar today.